Hello, just one moment while I get the slides shared. Okay, thank you for coming to my virtual talk. My name is Benjamin Elder. I'm a postdoc at Imperial College London, and I'm going to be talking today about how we could search for dark energy, dark matter, and modified gravity with the next generation of atomic clocks, the upcoming generation, I should say. This is work that I've done in collaboration with two PhD students in particular, at as well as a couple of postdocs and faculty members, all at Imperial. So the existence of dark energy and dark matter suggests that there's something new out there for us to detect. My background is in particle physics theory, and so I'm going to take the notion that this is some new type of particle. At the same time, it's becoming possible to perform atomic clock experiments with increasingly high precision over longer and longer time periods, up to years these days. So the question is, how can we leverage this technology to learn something new about the dark sector? So what sorts of clock experiments might we build, and what might we see? And the overall theme of this talk is that atomic clocks, particularly atomic clock comparisons, and I'll get into that in a moment, but atomic clocks are a remarkably general tool for us to explore new physics with. So, in case you're not familiar, an atomic clock is essentially a measurement of a particular transition frequency in an atom. And using an atomic clock can yield an incredibly precise measurement of time. Something like part in 10 to the 18 is not uncommon. The transition frequencies of the atoms, or a molecule in the case of a molecular clock, depend on fundamental constants. I'm going to put this in quotation marks because we'll see later on that new physics can make these constants vary, but they depend on things like the masses of fundamental particles or the fine structure constant. I'm going to be focusing in particular on the electron-proton mass ratio mu. And this ratio enters into the frequencies of different types of clocks in different ways. So you have optical, microwave, or molecular clocks, which all depend on mu, the electron-proton mass ratio, to some different power. So if all you have is a single atomic clock and that transition frequency is varying, you wouldn't know. Similarly, if you have two atomic clocks, but they're of the same type, then they would just vary together as mu varies. But if you have two atomic clocks of two different types, now you can use a comparison of them to be sensitive to variations in the electron-proton mass ratio. And if we have some new physics theory that causes these variations, then clock experiments are sensitive to it. So in this way, atomic clocks can be used to search for evidence of new physics. And the candidates that I'm going to talk about today are dark energy, which causes a linear drift in time, dark matter, which causes a sinusoidal variation in mu, where the frequency of that oscillation is proportional to the mass of the dark matter particle. And there's a modified gravity signal, which will give us a yearly signal as the Earth goes around the sun if the sun is sourcing the the um, the signal that we're searching for. And I'm going to talk about all of these signals in more depth later on, but in a nutshell, this is the main point of the talk. So if you get nothing else, this slide is the summary. Okay, so um, the new physics that I'm going to talk about is all going to be modeled in a minimal way with just a single real scalar field. And this scalar field may have some self-interactions, but of particular interest here is how that scalar field interacts with standard model particles. So we can put in either fundamental or effective couplings into the Lagrangian for our scalar field. And I'm going to work today at the level of couplings to electrons, protons, and neutrons. And I'm going to assume that the coupling to protons and neutrons is identical. It's controlled by this big M. You don't have to do this, but this is just a particular choice to let us um, make some statements that are not too overcomplicated. And then the electron coupling will be controlled by a separate parameter m sub e. Now, the thing that is interesting about this type of coupling is that it looks like a mass term for these fermion fields. So the total mass of a fermion is now the bare mass, the m sub e, say, for the electron, plus this correction phi over the coupling. So if so we have our fermions sensitive to the size of the scalar field. So if our scalar field varies in space or time, then the mass of that fermion does too, and that's what clocks are going to be sensitive to. So as I said, clocks are can give us a measurement of the mass ratio of, say, the proton to electron mass ratio. Um, so all we have to do is just write out the dependence of each of those fields in terms of the scalar field. And we have um, an expression for the kind of bare um, mass ratio, plus this correction phi over m effective, where m effective is the difference in the coupling strengths between, say, protons and neutrons versus electrons. So if you like, m effective is the degree of equivalence principle violation in our matter couplings, or the degree of non-universality um, in, in our coupling to the standard model. Now, I want to point out that for clocks to see anything at all, we do need some sort of EP violation. We need M effective to be non-zero. Otherwise, this effect, you can see from the middle line here that the scalar field part would just cancel out if MP equals ME. Okay, but if we have this field coupling differently to different matter fields, then this mass ratio now can in principle vary with the scalar field, and atomic clocks can see those variations. So I mentioned a couple of new physics scenarios for dark energy and dark matter that will give us particular signals to look for in a time stream of the electron-proton mass ratio. And one of the goals of this project is to identify particular pairs of atomic clocks that are both practical and useful for detecting those signals. The first scenario that I want to talk about is dark energy. And I'll model it as just a quintessence field, that is a scalar field that's just rolling down some self-interaction potential via phi. So cosmologically, this field only varies in time. And it has an equation of state that's given by the degree of kinetic energy in the field, that's phi dot, and the amount of potential energy in the field, V of phi. Now, because of Planck measurements, we know that the equation of state, W, needs to be between -1 and -0.95, and we know that the potential needs to be around 2.4 milli electron volts. Otherwise, there's just too much or too little dark energy. So what we can do is whatever our solution for the scalar field is, phi of t, then we can we know that it can't be changing too fast. Otherwise, the equation of state wouldn't be right. So what we can do is we can Taylor expand it in small t around the present day. And what we see is that the electron-proton mass ratio, mu of t, is varying roughly linearly with time. So if we measure a linear drift in mu of t, then we can potentially put limits on the equation of state of dark energy or the coupling strength of that dark energy field to the standard model. So here's what that can look like. I've got the electron pro coupling on the y-axis and the proton and neutron coupling on the x-axis. And these curves correspond to different amounts of dark energy, for different amounts of dark energy equation of state. So depending on what the equation of state of dark energy is, we can get stronger and stronger bounds up to negative 0.95, which is the clock bound. To get these curves, we picked two particular clocks, calcium fluoride and strontium, and assumed that we could run them at a particular uncertainty for up to 3 years. Um, for this type of scenario, the two clocks that I've picked are the strongest, but we did survey about 10 different clock pairs. For the dark matter type of signal, now we don't have a interaction potential V of phi, but we do have a mass for the scalar particle. So that's going to be little m here. And we don't know what the mass of the dark matter particle is. It could be anywhere in many orders of magnitude of electron volts. But if the mass is particularly light, then the field cosmologically just behaves as a classical oscillator. And we can uh, pick the amplitude of that oscillation to give us the correct amount of dark energy density today, dark matter density today. And the frequency of those oscillations is just given by the mass of the dark matter particle. So once again, this gives us varying mu, electron-proton mass ratio, um, and it gives us a sinusoidal signal that with the frequency matching the mass of the dark matter particle. We could also work through the algebra to calculate exactly what the amplitude of that signal is, and it's going to be based on the amount of dark matter density, energy density that's present today, the mass of that particle, and the strength of the matter couplings. Um, So just to summarize the main results for dark matter, there's a lot going on this slide, and so if you're really curious about it, please take a look at our paper. But the clock bounds are in blue and orange, well, and the dark matter particle mass is on the x-axis, and the strength of the EP violating couplings, that's M effective, that's the difference in the overall matter couplings, is on the y-axis. And I think the main points to take away from this slide is that first of all, clocks can be the state of the art for atomic clocks is incredibly impressive, um, which is why these curves are as high as they are. But also the width here is much wider than many other experiments are capable of. And this is deriving from the experimentalists that I'm working with believe that they can run these clocks for uh, they can derive good precision on clock frequency comparisons over a minimum time span of about 10 minutes and a maximum time span of about 10 years or 3 years uh, for this for this uh, for this slide. And this directly translates into a very wide mass range that is tested for the dark matter particle. And this is extremely complementary to atom interferometry searches. Um, Generally, the planned atom interferometry searches for dark matter pick up right where clocks drop off. So to the right of this, atom interferometry searches will really start constraining the dark matter mass range of about 10 to the minus 18 electron volts and up. So this is a sort of a coherent approach to accessing many orders of magnitude of dark matter particle masses. Finally, I want to talk about the third signal that I mentioned, and that's a modified gravity signal. So in this case, the scalar particle is not necessarily doing something cosmologically, although it could be present, and then the matter couplings in the field give us this signal anyway. Or it could be any type of generic new relatively light scalar field. So in this scenario, because the scalar field is coupled to matter, the sun sources a field profile that depends on the distance from the sun. And as the Earth goes around the sun, the Earth-sun distance varies at the level of a couple of percent. So the scalar field that the Earth sees varies as well. And so this is what gives us our oscillating signal in the electron-proton mass ratio, which is a precisely periodic on a period of 1 year signal. So in this case, we would take a time stream of mu as a function of t, and then try to fit a a 1 year sinusoid to it. We looked at several theories, a number of theories in this project. One of the best turned out to be the cubic Galileon, and I think if you're not familiar with the with this theory, don't sweat the details. But the main thing to know is that the fall off on the cubic Galileon can be like Newtonian gravity, where the field falls off as 1/r. But particularly close to a source mass, particularly close to the sun, where close is a function of the parameters of that theory, that fall off can become slower. So it becomes 1/√r in the case of the cubic Galileon. And this is an example of something called Weinstein screening. And depending on what the parameters, lambda and the matter couplings are, the clocks may see either of these two regimes. So the parameters that would be ruled out by this clock experiment are shown here in blue, along with existing constraints in gray. And those are coming from the microscope experiment and from lunar laser ranging. And the main takeaway here is that for sets of parameters where the Earth-Sun distance is outside the screened regime, so the field is unscreened, microscope is incredibly good at detecting that sort of theory. But on the other hand, once screening is active, clocks look to be a superior method of testing. Those clock bounds are currently subleading to lunar laser ranging. However, clocks are improving quickly, so that this situation may change in the near future. And this general trend of uh, clocks being a better way of searching for fields that fall off more slowly than 1/r is a uh, is one of the things that we found in this project. So here is a generalized interaction where the fall off with R is just a parameter of the theory. And here we found that generally the slower the fall off, the better clocks perform relative to microscope. Okay, I'm going to uh, wrap up very quickly now. Um, this talk really focused on some of the theoretical aspects, the new physics, um, but equally important parts of this project had to do with the experimental analysis and the time stream analysis for how we could actually extract the signal from a realistic experiment. And that was largely carried out by the PhD students that I collaborated with on this project. Um, the paper, uh, the paper for this project came out recently, and if you're particularly curious, you are welcome to download all of our code that we use to simulate the signal and extract the measurements. And I think I'll end there. Thanks, and I'm looking forward to discussing at the virtual conference.